Hey, June says that the sine and cosecant value of every acute angle is less than 1. Todd says that the sine value of every acute angle is less than 1, but the cosecant value is greater than 1. Who's correct? Well, let's go ahead and explore that with our 3 triangles from the getting started and from the previous page. Sine of 21 is easily calculatable with yellow calculator, with Desmos, whichever you're using. Sometimes, though, I will admit, your phone screen, that basic calculator isn't quite powerful enough as it stands. You have to do some of your own powerful mathematics to make it work effectively for you. But for us, I can go right into the trig button, type, enter, right, sine, and then do sine of 21 and get a decimal, 0.358. 0.358. Now that's definitely a number less than 1, so technically June and Todd are both correct. But yellow calculator ready to go. If we go over to cosecant, which is, come on, get there. Ooh, I'm in press to test mode. I need to get a different calculator. Be right back. Okay, this one should work. Trig, go over to cosecant and type 21 degrees. The cosecant of 21 is 1.195. So cosecant, CSC, of 21 degrees is 1.195. And right away, just with that example, June is wrong. Because June said that both of these should result in a number less than 1. And there it is. Cosecant of 21 is bigger than 1. Todd might be onto something. It's not really powerful enough for Todd to say every cosecant is going to have a value greater than 1, but we can, with just one example, but we can kind of make a stronger argument if we do a couple more. Let's do the other 2 angles. So we had sine of 35, and we'll talk about cosecant of 35 degrees. So trig, that's the button I'm pressing, get out of the glare. Sine of 35. This is in radian mode. I just realized that. So I need to go up and change. I haven't shown this to you guys yet. This is how you get these calculators out of radian mode and put them into degree mode. You come over to the little half of a gear with your mouse and you click on it. Then you go to document settings. And we want to change this from angle in a word called radians to a word called degrees. And lock it in, and I'll lock it in for all. So now I need to actually go back up and evaluate cosecant of 21. Cosecant of 21 is, clear it, menu 1, 5. We'll retype it and clear that too. Cosecant of 21, 2.79. Whoops, 2.790, not that number. And then sine of, the reason why I knew it was wrong, by the way, is for geometry, for you, our measurements are going to be positive. When you get to algebra 2 and beyond, we use radians. That's a different alignment of the same mathematics. However, by referencing a radian instead of a degree, we can have negatives. Trig, sine, 35, 0.573. The 3 is followed by a 5, which means that the 3 was rounded up to a 4. Now, cosecant of 35 is 1.743. So here's a second example where June is right and Todd is right, but because cosecant of 35 degrees is bigger than 1, June is wrong. So June is, wrong is such a harsh phrase, a harsh singular word, but we will establish not correct. June is not correct. Todd might be correct. Todd is probably correct. Let's go back to actually thinking about the fractions that gave us those values. And so when you look at the fraction for sine, it was 19.3 over 54. So I can put that here, 19.3 over 54. The cosecant is going to take that fraction and flip it. We would have 54 over 19.3. You guys, when you make a fraction where the top number is bigger than the bottom, your answer is bigger than 1. When your fraction has the bottom number, 19.3, bigger than the top, your answer is going to be less than 1. So Todd is correct. And it's all based upon how the hypotenuse is the longest side. It's going to be the biggest number. So I'll phrase it like that. The hypotenuse is the biggest number. I was going to say value. Denominator, numerator, wherever that hypotenuse value is placed is going to make that fraction flip to be bigger than 1 or less than 1. What happens to the sine and cosecant values of an angle as the measure of the angle increases? We already have that answer from page 565. The sine ratio is going to increase. But are you seeing how cosecant and sine are flips of each other, reciprocals of each other? If the angle is increasing and the sine ratio is increasing, then that means that the cosecant ratio will decrease. But I should also add right here something that isn't in the answer guide, but it lets me know where you should be thinking. Sine will increase to a value of 1. It'll never be bigger than 1. It'll never be equal to 1 in our geometry right triangle construct. Cosecant will decrease to 1. It'll never be 1. It'll never be lower than 1. In our geometry concept, cosecant will decrease down to a value of 1. But that's like a limiting number. Like it's I guess that's a calculus word. It's a limit of 1 for both of them. Just are we approaching from below or from above for that value? You calculated the sine ratios for different club faces in the getting started and in question 3 on the other page. So consider a golf club with a club face angle A, which has a sine of 45 or 0.45. Estimate the measure of the club face angle based on the decimal value. So sine of A, if it's 0.45, then we can use the ratios that we got from these 3 triangles to say 0.45 is between these 2 numbers. So it's going to be between the sine of 21 and the sine of 35 degrees, because that was 0.36 and this one was 0.57. It's like we're trying to trap the value, the ratio between 2 numbers we already know. In fact, that's what happened for centuries of not knowing about trig. There was someone whose job it was to make very accurate triangles, measure them, make the ratio of them, and then record it in a ledger so that someone else could look at that book and then know where their decimal was approximately located without needing to go calculate it all themselves. It's what a calculator is, but not digital because it's on a book. So for us, 21 degrees to 35 degrees is going to trap our decimal, which means we're probably somewhere between 21 and 35, like split the difference, like roughly 29, right? Somewhere between 21 and 35 degrees is our answer. And I'm going to just project 35 is closer to 36 than it is to 57. So we're going to be closer to 21 in our answer. I'm going to guess 28 degrees. Question mark. Now we can figure that out because we do have a calculator. So I'm going to go the sine of, sine of 29 and just see that's actually too high, right? Sorry that all of that's in the glare. The sine of 29 is 0.48. So I was a little high on this guess. I'm going to pick a different value. I'm going to pick 28. That's even closer. That's 0.46, 0.469. Let's go sine of 27. Sine of 27 is a really good, sine of 27 degrees is really, really solid. Okay. Use the right triangle to calculate the value of sine 30, sine 45, and sine 60, and leave your answers in exact value. I have put out a couple of shorts on these 2 triangles and the different angle relationships there are and the sine ratios that there are for those. So please check those out if you haven't already. No link in the description. Just go search through my stuff. You got this. Now, I'm still going to highlight our color scheme. So we have hypotenuse, hypotenuse, reference angle, opposite side, adjacent side. Oh, and up here, this must be 60 degrees because you do 90 minus 30 and you get the other angle. So sine of 30 degrees is opposite over hypotenuse. Sine of 45 degrees is opposite over hypotenuse. The nice thing about both of these fractions, and the way they're created, which is on purpose, is that this fraction will reduce. 4 over 8 reduces to 1/2, and 8 over 8 square root 2 reduces to 1 over the square root 2. And I made another YouTube short on that one about how to turn this fraction where the denominator has a square root into it into a rationalized denominator. But go watch that video. Go learn how to do that. But this is also equivalent to the rationalized denominator answer of root 2 over 2. Sine 60. That's the one that I saved for last on purpose because that's going to take the other reference angle. And it's going to flip theta from being here on the 30 degrees to now being located on angle B. And if you say the reference angle is now located here, this is no longer the adjacent side. It's now the opposite side. Opposite over adjacent, which is 4 square root 3 over 8. Opposite over hypotenuse. Opposite over hypotenuse. Sine is the ratio opposite over hypotenuse. This fraction reduces. Just like 4 over 8 reduces, the 4 and the 8 here reduce to root 3 over 2. These are all calculatable with your calculator to figure out the decimal they are. Leave your answers in exact values. Done. 1/2 is an exact value. Root 2 over 2 is an exact value. No decimals. Although they do have decimal approximations, this is written in the exact format. Last of all, question 9. 2 cables supporting the center pole of a circus tent are both connected to the top of the pole and staked in the ground. So, stake, top of the pole. The first cable is 30 feet long and the second is 46. So I see this number here and I'm going to go into the diagram and write that number in the diagram itself. I see the second number of 46 feet. I guess I'm dropping the feet units of measurement. I should probably put them back in. We want to make sure we're being consistent with our units of measurement and not mixing feet to yards, miles, etc., because then your numbers are off by that multiple amount. The angle formed by the pole and the first cable is 40 degrees. So I'm going to write 40 degrees in there. The angle formed by the pole and the second cable, wait a minute. I put the 40 in the wrong spot. That's the 40 degrees with respect to the ground. We need to put the 40 up here. And they do have that. Okay. The angle formed by the pole and the second cable is 55 degrees. So we got 2. Label the diagram, calculate the height of the center pole and the distance between the 2 stakes. So we don't know that one. I'm going to use all of this scratch paper you see in the background to answer this one question because it's going to take that time. But this is helping us solve real-world problems or a contextual sort of problem. Okay? So somewhere in the bottom of our window, that'll work. That will work. That'll do. Okay, so I'm going to draw the first triangle. I'm going to put in the information that we know. It's a 90-degree corner. There's 40 degrees up here and a 30-foot hypotenuse. So then if I label it, highlighting first, this is the hypotenuse. This is the opposite side. And then this is the adjacent side. Now in my second triangle, it looks like it's the little wedge, but I want to actually count all of this as my second triangle. So redrawing, same height, greater spread, and then 55 degrees up in the corner. So our hypotenuse, our opposite side, and our adjacent side. Highlighting really does help here, by the way. So if you're not highlighting on your diagram, you're giving yourself a handicap, or you're giving yourself extra things holding you back. Okay, so for us, we want to know the length of this side. I'm going to call that x. And I'm going to use x again, even though these are the same letter. I do mean to use them in different ways or with their own problems. So over here, the sine of 40 degrees is equal to the opposite divided by the hypotenuse. So x over 30. And if I multiply both sides by 30, we're able to solve for x. So, calculator work. 30 times sine of 40 degrees. That bottom side of the triangle's diagram is 19.28 feet. In this triangle, the same calculation. So maybe you should pause right now and try to do what I did for this triangle. You should do it for this one. And then unpause, and we'll work it out together. Okay, I'm working it out. Sine of 55 degrees equals x, the opposite side, divided by the hypotenuse, 46. This is the sine ratio. Now, multiplying by 46, multiplying both sides by 46, helps us isolate x. And now, this line, that x, has been solved for. So 46 sine 55. And I got 37, oops, sorry, glare. I got 37.681. So if I take feet, if I take these two numbers and I subtract them, we're going to wind up finding the distance between the two stakes. So by subtracting 37.681, subtract that, just right now hitting the minus sign, it's storing that answer and now going to use that number. So if I hit minus sign right now, it's meaning, oh, you mean the last number? Okay, I can do something with that. 19.2836. The distance between the stakes is 18.397 feet. Distance between stakes is 18.397 feet. To answer the question, calculate the height. We didn't do that, but we did do the distance between the two stakes. So I'm going to calculate the height now. And this is the nice thing about this with trig. Two ways. Pythagorean theorem is one of the ways. We now know how long that missing side length is. In fact, we know it for both triangles. And if you know two sides of a right triangle, Pythagorean theorem helps you find the third. We also have another way, and the other way is just make your reference angle go to the other one. This is a 50-degree angle. This is a 35-degree angle. And if you use our sine relationship, you can find the opposite side. I said Pythagorean theorem, so I'm going to do that first, only. Show me in class the other way to do that other way, the method. We know that in this triangle, a squared plus b squared equals c squared. That is the hypotenuse and the opposite side and the adjacent side. Since I know what x is now, as it's 19.28, but I don't know what b is going to be a question mark. We could substitute and work through. I'm going to go ahead and avoid that path right now. I'm just going to solve for b, no numbers, not yet. So first step in solving for b is isolating it by subtracting a squared from both sides. That's going to reduce that. Going to be 0. B squared is equal to c squared minus a squared now because I subtracted the a squared from both sides of the equation. We need b to be by itself, which means it's squared, and we need the square to be reduced, canceled. Square root will reduce or cancel a square. So then now the square and the square root are gone, and we have b equals. From this, we can now put in the numbers that we know. 30 is C. 19.28 is A. So those can go into this formula, and we'll know the length of B, the height of the pole. So 30 squared minus 19.28 squared, square rooted. All of this is now done calculator work, so I'm going to type it all into the calculator directly. I have the square root button, The square root symbol is yellow, and it's above the x squared button. So to do square roots on this calculator, I'm going to go second x squared, and I'm going to get that square root symbol. There's another way to find it as well, but this is the easiest way. Then I'm going to go 30 squared minus 19.2836 squared. And I get this. The height of the pole is 22.981 feet. 22.981 feet. With that, I have now answered all parts of question 9. Thank you for watching. Let me go ahead and end this right now so you can go ahead and get out of the video. But I appreciate you watching all the way through and for seeing how question 9 went. And I encourage you to click forward. We have more practice about sines and cosecants. And one more arc sine is coming up. Stick around.